In the next part of our videos, we're going to discuss the synthesis and reaction of esters. This is a fairly large section because esters have a variety of things available to them, but it mostly focuses on the interaction between the OR group either as a nucleophile or as a leaving group. Our first reaction that we're going to look at is the synthesis of esters from acid chlorides and acid anhydrides by essentially a nucleophilic acyl substitution. This would be what I had previously discussed about how derivatives that are further down on the chart could be made from derivatives that are higher up. We're going to combine the acid chloride and acid anhydride, representing them in this way with just Lg as a symbol for either chlorine in the case of the acid chloride or carboxylate in the case of the acid anhydride. Our observed reaction then becomes, start with our reactive derivative, put in an alcohol and pyridine. At the end of the reaction, what we will see is that the leaving group has been replaced by the OR prime portion of the alcohol, and the hydrogen has been removed from the alcohol. We use the symbol R prime here to indicate that the carbon group on the acid chloride or acid anhydride portion can be different from the carbon group on the alkoxy portion that we're putting on this side. We use pyridine as a base in this reaction to absorb hydrogen plus or remove hydrogen plus from the weak nucleophile after it reacts. We could use other bases. However, one of the advantages of pyridine is that it is not capable of forming a stable derivative if in the event that it were to react in place of the alcohol as a nucleophile. The mechanism for this reaction is shown here, and we can see that again it basically follows the SNAC mechanism. The only difference is that the alcohol is a neutral nucleophile, and as such, once it becomes attached, it gains a positive charge. So we have the alcohol reacting directly with the C double bond O carbon. We move a pair of electrons out of the way to make room so that we don't end up with 5 bonds on carbon. We make a tetrahedral intermediate. And the tetrahedral intermediate, as we discussed, has this electron pressure. It pushes back down onto the central carbon. It pushes out the leaving group. Again, chlorine is a much better leaving group than this protonated alcohol, so it would generally be pushed out rapidly. Carboxylate from an acid anhydride would probably be pushed out in preference to this. Would probably stay, and the nucleophile would get pushed out. We would establish an equilibrium, and then gradually, every once in a while, one of the carboxylates would be pushed out, and we would move in this direction. After the leaving group leaves, we have this intermediate, which, as you can see, is protonated and has a positive charge. And so this is where the base would come in. It would remove the hydrogen, the pair of electrons would go back on, and we would get our final product. Again, typically we specifically put in a base like pyridine to do this, but in our mechanism we don't have to specify the exact base. We can just use our generalized symbol for a base. Esters are interesting because they can also be synthesized directly from carboxylic acids. In other words, we don't necessarily have to start with a derivative and do SNAC. In this case, we would mix the carboxylic acid directly with the alcohol, and we would put in an acid catalyst. And by acid, again, what we mean is a strong acid without water. And what we would see is that we would form the ester directly and we would get water as a byproduct of this reaction. This observed reaction has been given the name the Fischer-Ester synthesis, and it's a very classical type of organic chemistry reaction. This reaction actually follows a very typical heteroatom exchange mechanism, a PRAM mechanism, where we have two phases. We first add the alcohol oxygen and then we remove the OH oxygen as water. So if we look at our mechanism then, typical PRAM mechanism, to add the alcohol we're going to protonate, then add, then make stable. So if we look at the first step, we protonate on the C double bond O oxygen. We get a protonated form of our reactant, which has a larger partial positive charge on the carbon, so that the alcohol nucleophile is more strongly attracted. It comes and makes a bond to that carbon, pushes a pair of electrons out of the way. That's our add. We get a protonated tetrahedral intermediate, which then can be made stable, getting rid of the positive charge by deprotonation with a base. So base comes over, moves a proton from this positively charged alkoxy piece, and we get this intermediate. So protonate, add, make stable. Now, what we're going to do is remove this hydroxyl group right there. To do that, we're going to first protonate to make it a good leaving group. We're going to remove it, and then we're going to have a make stable step, because again, this is going to result in a positive charge in our intermediate. So we protonate, pair of electrons comes out and grabs the hydrogen from our acid. We get this intermediate. That piece right there is now a good leaving group. It's a water attached to the carbon. So it breaks off, so we call that remove. We get this intermediate, and this intermediate, if we look, because we've removed a group, we have only 3 bonds. It's a carbocation, but it has this adjacent oxygen which can donate a pair of electrons down using resonance, and it actually becomes just a protonated form of our product. So to make it stable, the base will remove the hydrogen, a pair of electrons will move on to oxygen. That's the make stable step. We get our product. So if we were to summarize this, we're doing protonate, add, make stable, protonate, remove, make stable, PAM, PRAM. PAM, PERM, sorry. Now, one important aspect of this reaction is that it is an equilibrium. When we start with the acid and the alcohol, those are converted to the ester and a molecule of water under acid catalysis. So we can actually write the equilibrium out as a balanced chemical reaction like so. In order to get a high yield of the ester then, what we're going to need to do is either put a large excess of the alcohol to push the equilibrium to the right, or we're going to have to remove the water to pull the equilibrium to the right. If we don't take one of those steps, if we, for example, just mix stoichiometric equivalents here, at the end we would have a reaction that had not proceeded to completion. We would have a certain amount of the ester plus the water, but then we would also have a significant amount of the carboxylic acid and the alcohol unreacted. We can take advantage of the fact that this is an equilibrium to break the ester apart under roughly the same conditions. To do this, what we do is we start with the ester, we add a strong acid catalyst, and we add a significant amount of water. So we essentially add aqueous hydronium. Hydronium then is a strong acid plus water. We could write it hydronium aqueous plus water if we wanted to. In this case then, what we would see is that the oxygen of one of the waters would come over and it would replace the OR prime, the alkoxy group. The alkoxy group would be removed and protonated. So we would get a carboxylic acid and an alcohol. The mechanism of this reaction is essentially the exact reverse of the mechanism of the Fischer ester synthesis that we discussed above. In the notes, I suggested practicing this out, but because we don't have time to get together, I'm going to go ahead and write this out. Now, to do this, what we can do is we can start with the PRAM acronym for the forward reaction, which we said was PAM-PERM. In a reverse reaction, then, what we're going to do is flip that acronym backwards. So it's MERP, MAP, or whatever that is. But then, interestingly enough, in a reverse reaction, every make stable step in the reverse is actually a protonation, because in the make stable step, we're taking away a hydrogen plus. So the reverse of that would be to put a hydrogen plus on, in other words, protonate. So an M becomes a P. Similarly, a removal step becomes an addition step. If you're taking away in one direction, then you're adding in the opposite direction. So the R becomes an A, and then a protonation step in the forward direction becomes a make stable step in the reverse direction. So following this logic, then you can see how M becomes P, R becomes A, and so forth, and we get this acronym for the reverse reaction, which interestingly enough in this case is the exact same as the forward reaction. So then just working out the steps for that PAM-PERM acronym, we have a protonate step, so we protonate the ester on its carbonyl oxygen. We have an addition step, the water adds to the carbonyl carbon, moves a pair of electrons out of the way. We have a make stable step where base removes one of the hydrogens from the water that added. We then protonate on the oxygen that we want to remove, in this case the OR prime oxygen. So protonate. That makes it a good leaving group, so we remove it. We create again this carbocation-like intermediate, which has a resonance from the adjacent oxygen, which then makes it essentially into the protonated form of the carboxylic acid, and then base removes that hydrogen, and we get our product. We can also remove the OR prime group of an ester using aqueous base. This is called base-promoted hydrolysis, and we'll discuss why we use the term promoted instead of catalyzed in a little bit later after we look at the mechanism. This has also a very old common name. It's called saponification, because this is actually the chemical reaction that is used to make soap. And in fact, as a piece of chemical technology, this is ancient chemical technology. Soap making was known to the ancient Egyptians thousands of years ago. The observed reaction looks like this. We start with the ester, we put in aqueous sodium hydroxide, but we don't put in a catalytic amount. We put in actually one equivalent. I didn't put that in these notes, but it should say one equivalent. At the end of the reaction, we're actually going to get the carboxylate salt with sodium. And that's because sodium hydroxide deprotonates any acid product that we would form, because sodium hydroxide is a strong base. The alkoxy group becomes protonated because sodium hydroxide is not strong enough to 100% deprotonate that. So with lots of water, this becomes protonated. If we look at our mechanism here, we are not going to need to do a protonation step. So this is not going to follow a PRAM mechanism. Instead, this is more of a strong acid mechanism. It's basically a classic SNAC mechanism. So we have our nucleophile, which is hydroxide in this case. It reacts directly with the carbonyl carbon without any need for protonation. We get a full-blown tetrahedral intermediate, and then the electron pressure from that tetrahedral intermediate could either push out OR prime negative, or it could push out OH negative. Those two leaving groups have approximately the same base strength. So therefore, what's going to happen is there's going to be some of the time that OR prime would be pushed out and some of the time that hydroxide would be pushed out. So when hydroxide is pushed out, that just is the reverse of our first reaction. So we have an equilibrium here. We're going back and forth, back and forth. But in the case that instead of pushing out hydroxide, we push out OR prime, then we would move in this direction. Pushing out OR prime would create this product. Now, interestingly enough, in theory, it should be possible for this OR prime to react with the carbonyl carbon again and go back to our tetrahedral intermediate. But in practice, OR prime is a strong base, and the carboxylic acid is a medium strength acid. So therefore, it will do acid-base reaction more quickly than it would react with the carbonyl carbon in most cases. So therefore, what we have is a potential equilibrium where the reverse reaction is so much slower that effectively it just becomes one directional. We go this way, we deprotonate strongly. That is a very favored deprotonation. You can see K equilibrium is on the order of 10 to the 10th. And so this is our final product that we form. Now, this is called a base-promoted reaction because unlike a catalyzed reaction, where the catalyst 1 makes the reaction go faster, but 2 is not consumed by the reaction. In a base-promoted reaction, we do need the base in order to make the reaction go faster. So just putting water in would not cause this reaction. If we put water in at neutral pH, the ester would be stable for a long period of time. The water would be too weak of a nucleophile to do this first reaction at any significant rate. We put in the base to make it a stronger nucleophile. That makes this first reaction much faster, so it increases the rate of reaction. But we can see that we put in 1 molecule of base at the beginning, and we don't get that hydroxide molecule back at the end. So therefore, in order for this to proceed, we're going to need 1 full equivalent of hydroxide. In other words, the same number of moles as the moles of base that we're using. That's why this is called a promoted reaction.